today's presentation will be around 30 to 40 minutes with an additional 10 to 15 minutes of Q&A. All right, let's get started. Today's presenters are Richard Wood and Ariana Dribdahl. Rich is the Product Marketing Manager of Industrial Ethernet Infrastructure for Moxa Americas. For over 2 decades, Rich has worked in the trenches with plant engineers and OEMs to increase manufacturing efficiency through industrial automation solutions. He has contributed to successful implementations in automotive, semiconductor, textiles, packaging, and other industries. Rich's roots in lean manufacturing have contributed to his belief that these smart, connected factories are the foundation of data-driven process improvement. Ariana is the Product Marketing Manager for the Industrial Wireless Group here at Moxa. She possesses a wealth of knowledge when it comes to cellular and wireless technologies and understanding how to specify and deploy them within your network or system. And with that, I'll hand it over to Rich to get things started.
Thank you, Marty. So here's the agenda for today's webinar. We'll begin by introducing the smart factory concept and review some key market trends. We'll then discuss some of the top challenges in implementing a smart factory. Then Ariana and I will introduce some smart factory best practices. Finally, we'll wrap up with some case studies and answer any questions that you might have. Okay, so let's get started. The IoT, or Internet of Things, refers to devices, systems, and services communicating with each other via the Internet to enable smarter operations and new applications. The IoT spurred terms such as intelligent cities, intelligent highways, and smart factories. But what does that all really mean? So let's look at an example that many of you might relate to. For years now, many Department of Transportation agencies have used traffic cameras and ground sensors to monitor traffic and road conditions on our major highways. These systems were typically private networks accessible only to agency personnel at regional control centers. Through the Internet of Things, many of these sensors, cameras, and the data they create are now accessible via the Internet. The accessibility of this data has spurred the development of applications and services to provide better information to municipalities and drivers alike. In the past, the video and road sensors on a highway could allow someone in a control center to detect an accident and dispatch emergency services. Now those same video cameras, sensors, and other data can be shared securely over the Internet to allow local municipalities to more efficiently reroute traffic on surface streets near the accident and even alert drivers through their vehicle navigation systems or cell phones that there's an accident ahead and even calculate a route around the trouble. From a manufacturing standpoint, throughout history we've seen several technologies that have revolutionized how things are produced. The most recent being the introduction of the programmable logic controller in the late 1960s, which initiated over 4 decades of advances in industrial automation. We are now experiencing another industrial revolution, which people are referring to as Industry 4.0, or the Industrial Internet of Things. This refers to the connection of physical and cyber systems to build up a highly efficient smart factory. The smart factory brings together devices such as drives and sensors along with the machine-level systems such as PLCs that make up the production systems and connects them with the development, enterprise planning, and even point-of-sale systems in order to maximize production and supply chain efficiency while reducing defects and unplanned downtime. From a consumer point of view, smart factories result in more varieties made available faster and at a lower cost. Consider an online store where you can configure a laptop, automobile, or even an outfit to your exact specifications. Once you make your purchase, this information goes directly to the factory floor where your order is produced, packaged, and shipped the same day, often for the same price as a standard off-the-shelf model. From a production point of view, The smart factory provides a way to improve efficiency and reduce unplanned downtime. Data from temperature and vibration sensors on a machine, combined with the historical or statistical data, can predict when a component needs to be replaced so that it can be replaced during a scheduled routine maintenance rather than waiting for it to fail and shut down the line. Automated warehouses automatically organize incoming orders and route stock pickers through the shelves using the most efficient route. RFID tags and barcode scanners track inventory through the production process to final assembly and packaging and allow consumers to track their orders from entry to delivery at their doorstep. The factory of the future is a compelling vision, but unless you're building a new factory from scratch, the challenge will be connecting the various devices, systems, and production level networks together in a way that they can maintain their intended functions, yet communicate useful information to the other systems and networks. A common communication language or protocol is needed to facilitate these connections. That standard is Industrial Ethernet. Industrial Ethernet is now becoming the backbone for connecting legacy devices, control systems, and production networks to the enterprise planning and supply chain systems. As companies recognize the benefits of a connected factory and begin the journey towards implementation, there are some challenges to consider. The first is recognizing that most manufacturing engineers are not networking experts, and that the IT personnel at the enterprise level typically have little experience in the specialized needs of industrial networks. Since most of the manufacturing people are typically held accountable for keeping the factory running, the network equipment needs to be simple to install and configure with user interfaces that are familiar to what they're used to seeing in the production equipment and systems. The second is that industrial networks require much higher standards for reliability and availability. They need to be designed with redundancies so that the network cannot be taken down by a single point of failure. The components that comprise the network need to be designed to operate reliably in harsh environments found on the production floor, and they need to protect critical devices from unauthorized access. While an outage of 5 minutes in an enterprise environment may be inconvenient, it is tolerable and maybe even commonplace. In a production environment, an outage of less than a second can shut down an entire line. While these systems need to be designed to minimize the probability of network errors, in the event there is a problem, they also must be easy to troubleshoot and repair. This brings us to our first poll question. What are your biggest challenges in implementing a smart connected factory? Network security, network management, network availability or reliability, or integration with existing networks? Okay, so it looks like you guys are, it looks like integration so far is in the lead. We'll give you a couple more seconds to get your votes in. Okay. So it looks like half of you are concerned predominantly with integration with existing networks, with network availability and reliability and security being about tying for second place, and then network management being a distant third. Okay, well that's about what we see with most of the people that we've worked with in the past. So, well, let's dive into these things a little deeper. So based on our experience with other manufacturers, here's a model that we developed based on the priorities of production facilities to help in the design and deployment of industrial networks that connect those edge devices and control systems to enterprise-level networks, while addressing those main concerns that we outlined previously. So starting at the top, industrial networks must provide secure infrastructure with easy centralized management. They must have high system availability and be designed to operate in harsh environments found in many factories. And finally, they must integrate with the enterprise and other systems that rely on the information they provide. So let's look at some best practices for each of these elements. Cybersecurity has long been a concern at the enterprise level, but we've seen a dramatic increase in the number and frequency of attacks on critical infrastructure and manufacturing. These attacks come not only from malicious external hackers, but also from internal sources. When looking at security for an industrial network, there are two main concerns. The first is secure remote access to systems. As plant networks become more dispersed, it becomes necessary to provide for remote control and monitoring of critical systems while protecting them from unauthorized access. Industrial secure routers use encrypted VPN tunnels to provide easy secure access at a reasonable cost. The second is critical device protection. In a production environment, not only do you need to protect critical devices from unauthorized access, but you often also need to protect them from other devices on the network. For example, a malfunctioning PLC, if not properly isolated, could easily broadcast enough traffic to bring down the entire network. Industrial firewalls can provide the proper protection and isolation necessary. These firewalls are specifically designed to filter the types of traffic harmful to industrial networks. They are also designed to be installed without having to reconfigure the rest of your network, unlike many of the enterprise firewalls. When it comes to implementing and configuring an industrial network, individually configuring multiple devices located throughout the factory can be frustrating and time-consuming. If you've ever had to walk from control cabinet to control cabinet using a laptop to configure networking devices, you know that it's hardly efficient. But luckily, with today's managed devices and remote configuration and management tools, it is possible to install the hardware, then configure and verify everything from a single remote location on the network. In a recent case study, a systems integrator we work with found that they could cut their configuration time by 90% in using these tools. Once installed and configured, industrial network management systems allow centralized management, backup, recovery, and troubleshooting. These systems are similar to enterprise network management systems, but with a few important differences. Enterprise network management systems are designed for IT experts, not industrial engineers and maintenance personnel. They provide lists of technical data and show the logical links within a network, and typically only give you periodic data about the network health and the health of the devices on the network. Industrial network management systems, on the other hand, are designed with factory personnel in mind. They show visualizations of the physical network topology and devices right on down to the port level, and provide real-time alerts for defined events. They can even compare snapshots of the network in a healthy state when a problem arises so that you can quickly pinpoint and change what changed and fix it. These features are critical when faced with a potential shutdown situation. Which brings us to our next poll question. Do you currently use a network management system? Why don't you go ahead and put your vote in. It looks like the vast majority of you have not used a network management system, but would like to. We'll give you a few more seconds to get your votes in, and then we'll take a look at the results. Okay. So clearly 80% of you have not used a network management system, but would like to. 13% of you use an enterprise level network management system, and only 7% use an industrial network management system. All right, well with that, I'm going to turn things over to Ariana, and she'll take you through network availability and reliability.
Thanks, Rich, and hello everybody, and thanks again for joining us today. As Rich mentioned, I'll be taking you guys through a few more kind of best practices for network availability, for the smart network. So I'm going to talk a little bit about network availability and reliability, then move into rugged industrial design, and then finally a few slides of system integration, and then followed closely by some case studies. Now this slide here shows what's been kind of going on in a typical factory. This is what we call our star topology. A star topology is one where we typically have one point of failure, which means that all of these other nodes that are connected on the network essentially all filter through this main node here. Now if that node happens to go down, that can create big problems because that essentially cuts ties to every single one of the remote nodes that have been currently wired into that one. In addition to that, this type of topology also has long, very costly fiber or wire runs. So it tends to be very costly to implement, but it also can be very costly from an availability perspective if that one single node goes down. Since there has been a lot more emphasis put on network availability and reliability, in recent years a ring topology has kind of emerged as a best practice, if you will, in terms of wiring up your network for availability. So within the typical ring topology, as you can see, each individual node is wired to the preceding and the following nodes. What this means is that if you have any kind of a failure at any one of those nodes, there is still an alternate path that basically will go around the entire network to have its data still reach its destination. So no longer do you have that single point of failure. You now have a much higher availability and a much better chance of your data going to where it needs to go if you have that point of failure. In addition to that, since you're not hardwiring directly from one master node to each remote node, you save a tremendous amount on wiring costs as well. The amount of cable runs that have to take place is going to be significantly reduced from the previous star type topology. Now, once you have chosen a redundant type of topology, it's important to note what type of redundancy you want. Now, we classify these as three kind of typical cases. One is non-time critical, one is real-time, and one is isochronous real-time. The types of applications for each of those differs, of course, depending on the amount of recovery time that needs to take place. We typically classify the non-time critical applications as ones that are okay with any kind of recovery time less than 1 second. These are going to be any kind of non-time critical applications, or applications in which if your network goes down for around a second, you won't have serious implications. We move then into real-time, and real-time redundancy is what's typically classified as less than 100 milliseconds. This is very common in factory environments for process or factory automation. These types of applications do have the ability to have a little bit of flexibility in terms of the recovery time, but that's typically going to be no longer than 100 milliseconds. Finally, the isochronous real-time, which is less than 1 millisecond, is for extremely mission-critical type applications like motion control. So if you can't afford to have any kind of downtime, then this is the type of redundancy that you're going to want to look at for your network. Typically, what we recommend when we talk to people about redundancy is we recommend that the network switch recovery time is going to be less than your maximum acceptable system downtime. And we also call this grace time. Now this is an example that we like to show, and this is essentially a control system that is communicating with PLCs. And those PLCs are in communication with the control system approximately every 50 milliseconds, and that's just to check system availability to make sure everything's up and running properly. Now, if the network recovery time were to be larger than 50 milliseconds, then the control system would basically treat the PLCs as malfunctioning or in a malfunctioning state. If that state is then detected, it will basically shut down the entire system to prevent damage from a production line. Now, in that same scenario, if the network recovery time happened to be less than 50 milliseconds, then the control system will still communicate with the PLCs normally. What this means is you won't have any shutdowns and the system will continue without interruption. In this type of case, we say this is basically a real-time redundancy requirement. Now, there are two types of redundancy that can take place within this. There's what we call our mesh and our ring. The ring, of course, being the example that we just showed. This goes into a little bit more detail about each of these types of redundancy. So there are pros and cons of each. Mesh is it's a good reliability. It has very high resilience, and one of the biggest benefits of that is that it's a standard protocol, meaning it is interoperable between different vendors of hardware. One of the downsides of a mesh type of a topology is that it has a very slow recovery time, so it's basically on the second level, so it's not really appropriate for any kind of real-time redundancy requirements. The technology is called RSTP, or Rapid Spanning Tree Protocol. And this is typically used in more of a commercial environment or an office environment where it's okay if your network goes down for 1, 2, 3 seconds. Again, what we're seeing a lot more in smart factories is this ring level topology for redundancy. And on this type of topology, you're talking millisecond level recovery time, and it also tends to be a lower cost. Now, the problem with ring type topology is that A, you have limited scale, and B, these are typically isolated to a single hardware vendor, which means that if you have different vendors of hardware within your factory, you typically can't use this type of topology with those vendors together. Now, there are some standards that we call general standards, and they're fast recovery. And again, RSTP at 20 milliseconds. So, you can see definitely the difference. And of course, that ring topology is a lot more appropriate in any kind of industrial or more mission-critical applications. Now, another best practice for having, availability is to make sure that you have a very fast boot up time on the devices that are running on the network. What we've seen is that a typical boot up time for a PLC is going to be roughly around 20 seconds. Most switches, especially those on the commercial or the enterprise side, will take anywhere from 40 seconds to about 1.5 minutes to boot up. And that's significantly longer than a common industrial PLC. If you compare that to industrial Ethernet switches, which typically will have a boot up time of around 10 seconds, you can see that's a significantly faster boot up time. Now, what we typically recommend for best practice is that the time for switches to boot up should be shorter than the PLC in order to make sure that the stability of the network is in place. Now, this is especially important with safety PLCs that will basically shut down the entire network, the safety network, if the network devices are not already up and running. Some of the benefits of this, of course, the higher system availability and the lower maintenance cost, and then, of course, prevention of unnecessary alarm messages. So it's very key when you're selecting a piece of hardware or an Ethernet switch for your network that you always want to make sure you know how much the boot up time is, again, as that will affect the other devices on your network. Now, there's a lot of people who also want to integrate wireless into their facility, and wireless has been a very hot topic lately. You have people who absolutely love it and who implement it everywhere they can, and then you have those people who are kind of hesitant to try it because they're not sure about the reliability or the availability of it. For those of you who haven't checked out wireless in the last few years, there are a lot of different, advances that have taken place within the wireless protocols that make wireless a lot more reliable and a lot more available than it was in the past. One of those ways that wireless has become a lot more available and reliable is seamless communication. You may also hear this referred to as roaming. In this type of standard, it basically allows any mobile devices, for example, an AGV within a warehouse, to be constantly connected to a wireless network. The way that it does that is that these devices that are connected to the AGVs, we'll call them clients, they essentially will be constantly scanning for a stronger network or a stronger network signal from another access point. Now, when the access point that they're currently connected to reaches a predefined threshold, they will basically try to authenticate to that second access point while still connected to that first access point. Then what happens is, as they're moving away from that first access point again, they're already connected to that second access point, and that allows them to switch over very, very rapidly. In this way, you basically don't lose much time at all when you're switching from access point to access point. Now you contrast that with the way that wireless has been in the past. If you do not have a roaming optimized device, it can take anywhere from 5 to 10, even 15 seconds sometimes to move from one access point to the next. The reason for that is because those devices typically will need to completely disconnect in order to reconnect to a new network. So having this seamless communication and roaming technology allows those devices to be connected at a constant time. In terms of reliability, there have been new advances which allow zero packet loss when you're talking about wireless communication. And what this is it's basically a redundant wireless type of a technology. Now, traditionally in the past, there has been only a single RF or a single radio device. And what happens is when something comes and interrupts that transmission, whether it be from interference, whether it be from a network loss, what have you, basically that entire wireless network can go down. Now, to get around that, there are available nowadays what are called dual RF or dual radio devices. And what happens with these devices is you have one radio that transmits on one frequency, say 2.4 gigahertz, and you have a second that transmits on another frequency, for example, 5 gigahertz. Now, if you get interference, for example, on that 2.4 gigahertz network, because you're still broadcasting on the 5 gigahertz network, that data is still able to go through. So it makes the packet loss pretty much close to zero when you use this type of technology in a wireless environment. Now again, this slide just shows a summary of what I talked about. Again, you have that active concurrent connection going between a redundant access point and a redundant client. That redundant client basically will do a packet analysis on the data that's coming through from both of those signals. It says which has the best RSSI, it says which has the best signal-to-noise ratio, which has the lowest latency, and it basically will pass on that better signal and discard the worse one. Now again, if that worse one happens to go away, for example, from interference, then it will pass on what used to be the worst one, which of course is now the better of the two options, and it constantly monitors that signal. So it's time for our last poll question. Do you currently use wireless in your plant? So we got 4 choices for you in this question. The first one is no, but I would like to. The second one is no, I don't really have a need for wireless at this time. Yes, we do currently use wireless, but only for non-critical systems. And yes, I love wireless. Let's use it everywhere. So it looks like you guys are filtering in some answers here. Looks like quite a few of you actually use wireless. Wireless for non-critical is what's in the lead right now. I'm going to give you guys a few more seconds to vote here, and then we'll show you what we got. All right, so here are the results. So it looks like lots of you love wireless, which is something that I always like to hear, given that I love wireless as well. Most of you, 46%, are using wireless within your facility already, but only for non-critical systems. 24% of you are using wireless pretty much everywhere you can, and the last 30% of you don't use wireless, whether it be because you don't have a need to or because you just haven't gotten it implemented. So thanks everybody for voting in our poll. So now I'm going to talk to you guys a little bit about robust industrial design and some of the best practices and some of the benefits of using that as opposed to traditional commercial or enterprise level hardware. So harsh environments tend to be very, very different from an office environment. That may seem like an obvious answer or an obvious statement, I should say. However, there are still a lot of people who don't realize that there are these big differences between the two. You have in an office environment controlled temperatures, controlled humidity, and controlled air quality. So it's great for enterprise level products that aren't built to withstand anything more than the rigors of a controlled control center. You contrast that to industrial or factory environments where you may have things like severe vibration or shock, high humidity, high pollution. Some places even have washdown. You have a lot of electromagnetic interference that can occur from devices that are operating within these factories. And again, they can be either hot or cold. A lot of factories are not air conditioned or they're not heated. So when you get into Texas during the summertime, or Minnesota during the winter, that's going to be significantly hotter or colder than your traditional, temperature controlled control center. So there are things that have to be taken into account in terms of building and developing these types of products that will allow you to withstand those types of environments. Now, most industrial devices that you're going to use in these types of environments are literally built from the ground up, whether it be down to the capacitor level, to the cooling that's built into the units. Most of these devices are not fan-cooled. They are going to be just air-cooled and using heat sink technology, and that will allow these devices to operate in even very, very extreme conditions. We've seen them operating everywhere from a pipeline monitoring system in Russia, which reaches temperatures of -40 Celsius in the winter. And I don't know about you guys, but I would not want to be anywhere near a -40 degrees Celsius temperature range in the winter. But industrial hardware loves it. They don't have any problem with it. Same thing, all the way up to the drilling in Saudi Arabia, which goes up to 75 degrees Celsius in the summertime. Extremely hot. It's not an environment that any human would want to be in for any sustained period of time, and yet these industrial switches are able to function in this type of environment very, very easily. Of course, you would never want to put any kind of commercial or enterprise level devices into these environments because you would see multiple failures on a pretty rapid level. Now, the final topic that we want to talk about is integration with control level networks, or system integration. So there has been, a very big trend into integrating legacy devices or different types of networks into a plant floor network. Rich kind of talked about it in one of his poll questions, and it seemed like a lot of you guys were concerned with system integration. So I want to just take a couple slides to talk about how you can do that a little bit easier and more efficiently. Now, a lot of people want to integrate some sort of SCADA system into, a plant floor or a control or field level type of a network. Now, there are a lot of different types of industrial protocols that are on the market, some of the most common ones being Profinet, Ethernet IP, and Modbus TCP. Now, these networks on their own are wonderful, but if you have devices that have the ability to bring those into an enterprise or into a plant-wide network, you increase the amount of efficiency that you have for your network. Now, there are a lot of industrial automation specific switches that actually enable these protocols by default, which makes them plug and play. Now, that's not typically a statement that you would associate with any of these industrial protocols. However, these switches and these devices make it really easy to actually integrate those protocols into a plant-wide network, essentially by setting, presetting a different parameters that you would normally need to run those types of networks already in the switches when you purchase them. So there's a lot less configuration and a lot less effort that has to be put into, the IT or whoever is managing that plant-wide network. Now, we do also see a trend to integrate from the device level all the way up to the enterprise level. More and more people are trying to do top floor to shop floor, as we like to call it, which means that their commercial or their IT department wants to operate everything from the offices all the way down to the plant floor and make it easy to manage and to see what's going on at all of those levels. Now, we typically, when we say a field level, we say, this is basically a device server, so serial-based products like sensors, actuators, or remote I/O. You also can integrate the control level networks, and we typically refer to those as PLCs, PACs, drives, or CMs. This is where kind of the sweet spot for, what we call our real-time redundancy Ethernet that we talked about is. On the operator level, we typically refer to devices like HMI and SCADA, and then finally, of course, on the PC level or the office level, we're talking pure Ethernet alone. So having switches and devices that support or allow you to bring those types of protocols all onto the same network is a very good way to increase the availability of all devices on the network at all times. So we're going to wrap it up here, guys, with a couple of case studies. One's going to be on the wired side and one is going to be on the wireless side. So on the wired side, this is actually a fairly typical type of an application that we've seen. This one is specifically for a semiconductor plant. They basically wanted to invest in thousands of dry pumps for an exhaust systems to protect the workers who are working there from those gases that are produced during the semiconductor fabrication. They also wanted basically a way to simplify not only the pump system control and monitoring, but also a way to basically integrate and see the entire network at any given time. So what they ended up choosing was an NMS, which allowed them to use their SCADA system. So they were able to tie into their SCADA system. They were able to monitor the work with that NMS system and basically give a real-time overview of what was connected, what was down, what was working, what was not working at any given time. Because they transfer very large amounts of information, they also wanted to have gigabit Ethernet ports. And they basically used a ring topology. If you remember, we talked about that a little bit earlier today. But they used that ring topology to basically form a redundancy network that would allow them to have less than 50 millisecond redundancy or recovery time if any one of those Ethernet switches went down. On the wireless front, there was an application that we've seen. This one actually comes out of Europe, and they were looking to make their factory more mobile. So they had a lot of AGVs that they wanted to network, and they wanted to be able to keep track of at any given time to basically increase the efficiency of the day-to-day goings of this factory floor. So they decided that using a wireless technology with high availability and fast roaming would really, really fit their needs. And the reason that they chose this was that it would have been extremely expensive for them to wire, not to mention nearly impossible to hardwire any kind of a moving vehicle like an AGV. And they were concerned about security, so they also did enable wireless VLANs, which is something that is supported in most industrial, as well as a lot of commercial enterprise level wireless devices. But this allowed them to basically isolate the wireless network from the rest of their network without worrying about the wireless potentially degrading or being detrimental to the existing network. And with that, I'm going to turn it back over to Marty, and we're going to do some Q&A. So thanks, guys.
All right, thank you, Ariana. Okay, we're going to open it up for some questions now. It looks like this first one I have is from Susan. Susan asks, what are some of the most common failure points in an industrial network? So I think Rich, I think that makes the most sense for you to take, so I'll hand it over to you.
Sure, thanks, Marty. So the two most common, I guess, points of failure that we see in industrial networks is the first is power supplies, and the second would be anything mechanical, so fans typically and industrial switches. That's one of the main reasons why we eliminate fans in all of our switches, because it's the leading cause of failure. And most industrial switches these days also have redundant power inputs, so that if you do have a power supply failure, you have a backup already connected and you get an alert so that you can change out that power supply before your backup fails. So hopefully that answers your question.
Great, thanks, Rich. This next question, it looks like I have from Tom. He wants to know what can I do to make sure my wireless connection is free from interference. So wireless, Ariana, I'm going to hand it over to you.
Thanks, Marty, and thanks for the question, Tom. It's a great question. There are many things that you can actually do to help avoid interference. When we talk about wireless interference, there's basically three things, or three types of interference. We call them narrowband, broadband, and co-channel interference. Narrowband typically isn't something that affects wireless performance, but the two biggies that we do need to be concerned about are broadband as well as co-channel. Now, broadband is considered to be any kind of interference that comes from an external source that's not another wireless network. It could be anything within a factory. It could be, a motor that's spinning up. It could be even something as benign as Bluetooth or even a microwave oven, believe it or not. Microwave ovens tend to be extremely detrimental to wireless networks. So what we typically recommend is you make sure that your wireless networks are not in the vicinity of anything like that. So if you have a lunchroom on the opposite side of a wall where you're looking to place wireless, perhaps that's not the best of ideas if there's an industrial microwave there, for example. If you have any additional devices that are going to create a lot of noise, you want to maybe try to isolate your network or put it away from those devices. But the biggie is actually co-channel interference, and this happens to be the biggest issue with interference within wireless. Co-channel interference is basically classified as any kind of interference that comes from other wireless networks in the area. Now, a lot of people don't realize, but when you're talking about 2.4 gigahertz, which is the most common frequency used for Wi-Fi, within 2.4 gigahertz, there are only 3 channels that don't overlap, and pretty much every manufacturer in the world will set their devices by default to one of those 3 channels. Those are 1, 6, and 11. And, you know, as a consequence, those channels tend to be extremely saturated in terms of wireless networks. So if you want to avoid the interference from those networks, there's a couple things that you can do. One is to do basically a site survey and to take a look at what other devices or wireless networks are in the area. Now, you can use any kind of site survey tool. Some phones even have it. You can get it. You can get some online. A lot of people have corporate ones, but it's just a good way to basically see what channels or what frequencies are already being in use and plan your wireless network around those frequencies. The other thing that you can do is move your network to 5 gigahertz, and this is something that we've been seeing a big trend in with the industrial space, is a lot of people moving to 5 gigahertz. It tends to be a lot less susceptible to interference from not only a co-channel but also a broadband perspective, and it also tends to be a lot less crowded. So those are 2 ways that you can kind of help avoid that.
Great, thanks so much, Ari. The next question I have is from Kalen. His question, it may be a little bit more Moxa specific, but maybe hopefully we can elaborate to include more switches. But his question is, what is the longest time that a Moxa managed switch, I'll open that up to include managed switches in general, should take to boot up? So I'm going to actually pass that back to Rich. I think that's right up your alley. Go for it.
Thanks, Marty. So we break down switches into a couple of different categories. Basically layer 2 switches, we typically guarantee that they'll boot up in 15 seconds. Typical, it's less than 10 though in actual practice. When you move to a layer 3 switch, you know, more of the rack mount switches you'll see in a control room, those take a little bit longer at typically 25 seconds. The only other type of product that typically takes longer than that would be the industrial routers. Industrial routers do run off software, and so much like your PC, they take a little longer to boot up, typically between 1 and 2 minutes. So you know, typically we recommend that typically at the shop floor level where you're integrating with the types of equipment that needs a fast boot up, you're typically dealing with a layer 2 edge switch, so you're at less than 15 seconds. You know, certainly if you're using an industrial router, you want to make sure that it's placed in a way so that it has the time to boot up without interfering with your critical devices.
Great, thanks, Rich. This next question from Mike, he asks, if I already have one network vendor in my plant, do I need to continue using their technology to have a redundant network? So maybe, I think that's another one for you, Rich.
Sure, that's a great question. We run across that all the time. In fact, it's fairly common, typically when you're interfacing with the enterprise level networks, that kind of that control room might use an RSTP protocol, but that as you get out into the factory itself, you need you know, faster recovery times. So you know, Moxa has a chain technology that works very similarly to the ring, but it also allows you to connect to other types of redundant technologies so that you get the fast recovery in the parts of the network that you need it without having to convert the entire plant to a specific protocol.
Okay, great. Thank you very much again, Rich. This is the last question I have, unless we get any more in, but this one comes from John. He asks, on the industrial firewall, you mentioned you don't have to reconfigure the rest of my network. Can you perhaps elaborate on this? And I think, Rich, I'll pass it right back to you.
Sure. Another great question. You know, typically the way firewalls work is you have a different subnet on either side of the firewall, And so traffic coming from one subnet through the firewall gets filtered based on the rules that you set up and then allows the traffic that matches the criteria you've set onto the other subnet. So in an industrial situation, for many reasons, one being you're typically dealing with as I mentioned earlier, a plant engineer who may not have an extensive background in network IT. You don't want to have to reconfigure every device on the other side of a firewall to a different subnet. That's just a lot of extra work and complexity that can get in the way. And often, there are parts of the network that certainly your IT department is not going to be happy about you trying to modify subnets within the building. So we have a technology called transparent firewall, and that simply allows you to place a firewall device anywhere within a network, not having to reconfigure the subnets on either side, and it will filter the traffic based on the rules that you set. It makes it very easy to set up kind of a tiered security topology within your plant.
All right. Well, with that, I'd like to thank Rich and Ariana, and thank you to everyone for your interest and participation.